In the next two lessons, we're going to look at metals and non-metals, and we're going to compare their physical and chemical properties. Okay, so there's a sort of standard dividing line in the periodic table which divides the metals from the non-metals. And the best way to do that, if you can remember this, is to draw a stairway starting here just to the left of boron, and then you're going to draw the stairways downwards. Okay, what we've got is what we class as metals are to the left of that stairway, and non-metals are to the right of that stairway. So to kind of understand the difference between the two and how this, stairway sort of comes about, what we need to do is try and understand exactly what we mean by a metal. What is a metal? And then once we can understand what we mean by a metal, then we can understand what we mean by a non-metal. Okay, and then you should be able to see where this stairway comes from. So what is a metal? Well, a metal is an element that is able to lose either all of its or some of its outer electrons, okay, that's the electrons in its outer shell, in order to obtain a stable structure. Okay, we'll just look at how they do that in a minute, but let's just take, for example, three examples from period 3 of the periodic table. So we'll take sodium, and then magnesium, and then aluminium. And you'll remember that sodium has one electron in its outer shell, whereas magnesium has 2 electrons and aluminium has 3 electrons. So when these atoms combine with other atoms of their kind, that's to say when sodium combines with other sodium atoms, or magnesium with other magnesium atoms, what they're going to do is they're going to lose their outer electron. So sodium will lose its outer electron, magnesium will lose 2 outer electrons, and aluminium will lose 3 outer electrons, and that will result in a positive sodium ion, and in the case of magnesium a 2+ ion, and in the case of aluminium a 3+ ion. Okay, in order to obtain a stable structure, that structure of positive ions will look like this. So in this case, these are the sodium ions because they have only one positive charge, and the electrons which the sodium ion loses, these are called delocalized electrons. These are made available to surround the giant structure of positive ions. Okay, so these are a sea of delocalized electrons that surround the positive ions, and they help to hold them together. So if these delocalized electrons weren't there, well, you can see that where you've got positive and positive charges, the whole lot would simply fly apart. But the delocalized electrons, this sea of electrons which have been donated from the original atoms of the metal, play a role in keeping this positive ion structure together. Okay, so in the case of magnesium, then each of these ions would have a 2+ charge, and there would be twice as many delocalized electrons surrounding the ions, holding them together. Or if it were in the case of aluminium, then each ion would have a 3+, etc., and there would be 3 times as many electrons available to hold the ionic structure together. Okay, so the point is that metals are made or come into existence because the atoms are able to lose these outer electrons. That's what enables this structure to take place. So the atom's got to be able to lose either all of its outer electrons, or at least some of them, in order to form positive ions, and then these electrons are then used to hold the whole thing together. Okay, so let's just return to the periodic table to summarize that. What do we mean by a metal? Well, a metal is an element from this periodic table that is able to lose either all of its outer shell electrons or some of its outer shell electrons in order to form a positive ion, and those positive ions are then accumulated into a giant ionic structure, as we've just seen, which is held together by a sea of delocalized electrons. Okay, it looks like it's got measles, doesn't it? But these represent delocalized electrons. Okay, and these come from the outer shell electrons that were lost by the atom as it ionized. So a metal is an element that is able to do this, and the ability for the elements to do this, as a general rule, decreases as you move along each period of the periodic table. So, for example, sodium finds it very easy to lose its outer shell electron, looking at period 3. Then magnesium, which has to lose 2 electrons in order to get a stable structure, finds it energetically harder to lose its outer 2 electrons. And then aluminium finds it energetically even harder to lose its 3 outer electrons to get the stable electronic structure. And then what happens is, as you pass this boundary that we drew at the start of this lesson, then the elements are no longer able energetically to lose their outer electrons. And we then call these elements non-metals. So we can say a metal is able to lose its outer shell electrons, while a non-metal is unable to lose those outer shell electrons to form positive ions. So the question then is, how do the non-metals combine with themselves to obtain a stable structure? To answer that question, let's take a couple of examples of non-metals that we're familiar with from the GCSE syllabus, for example carbon and fluorine. How do carbon atoms combine with themselves to form stable structures? How do fluorine atoms combine with themselves to form stable structures? Okay, so what we're saying then is that carbon, which is in group 4 of the periodic table, has 4 electrons in its outer shell, while fluorine, which is in group 7 of the periodic table, has 7 electrons in its outer shell. So these elements are simply unable to lose their outer shell electrons to form positive ions. So they are unable to become metals because they cannot lose their outer electrons. So instead, what they're going to do is they're going to share their electrons in the form of covalent bonds, and this will enable them to obtain a stable electronic configuration. So metals lose their outer electrons, while non-metals share their outer electrons to form covalent bonds. And there are 2 types of covalent structure that the non-metals will form. The first is what we call giant covalent structure, which is in the case of carbon. So what happens is carbon here shares its 4 outer electrons with the electrons of other carbon atoms. So each of these 2 shared electrons here in the overlap between the orbits represents a single covalent bond, and again this carbon atom will do the same with another 4 carbon atoms, and likewise with this one. So what we've got to remember here is this is a 2-dimensional representation of what is actually a 3-dimensional structure. If we look at the 3-dimensional structure, then the carbon atoms join to form a giant molecular structure that looks like this. So this kind of tetrahedral structure spreads throughout the whole system. But the important point is here is that what the carbon atoms are doing is they're being joined by covalent bonds, and this forms what is called a giant covalent structure. So that's one of the ways in which the non-metals will combine with each other to obtain a stable structure, using covalent bonds. Now, the other way in which non-metals will combine with each other is in the form of what is called simple molecular substances or structures. So for the case of fluorine, again, which has 7 outer electrons, it shares its 7th electron with the electron from another chlorine atom. There we have the dot and cross diagram, okay, and there where these 2 electrons from each fluorine atom are shared, that forms one single covalent bond, and the fluorine then exists as a simple diatomic molecule joined by one covalent bond. So this is the other type of structure that you'd expect in the non-metals. So this diatomic structure here, which you see in fluorine, is repeated right the way down the halogen group. They all form these diatomic molecules. Now, these diatomic molecules, although the atoms are held by quite a strong covalent bond, because the actual covalent bonds in themselves are strong, the molecules themselves are held together by what is known as intermolecular forces, and these intermolecular forces are weak. Okay, so let's just look at that. So here in the case of fluorine, we've got strong covalent bonds holding the atoms together, but in between the molecules of fluorine there are also forces which are acting between the molecules, which are called intermolecular forces, which are much weaker than the covalent bonds. So in the non-metals, we expect to find 2 types of structures prevalent. Both of these involve covalent bonds. One of these is the giant covalent structure, an example of which is depicted here, which shows the structure of diamond, which is an allotrope of carbon, and the other is the simple molecular structure or substance, which you'll find in the group 7 elements. Okay, just to summarize then, metals are elements which are able to lose all or some of their outer shell electrons in order to obtain positive ions with stable electronic configurations. When they do so, they form a giant ionic structure which is held together by a sea of delocalized electrons. And this is really important in the next lesson, where we look at the properties and characteristics of metals and non-metals. So non-metals, on the other hand, are elements which are unable to lose their outer shell electrons because it requires too much energy. It's energetically uneconomic for them to do so. So instead, they take the option of sharing their electrons to form covalent bonds. So instead, they obtain stable structures or stable electronic configurations by sharing their electrons to form covalent bonds. And we saw that the non-metals can adopt 2 types of covalent structures. One is the giant covalent structure, for example, in the case of carbon, silicon, and the other is the simple molecular structure, as in the case, for example, of the halogens, oxygen, nitrogen, etc. So, in the next unit, what we're going to do is we're going to look at the properties and characteristics of metals and non-metals, and we're going to see how the electronic structure and the type of bonds that hold them together influence directly those characteristics and properties.